Hey everybody, I'm here again with Paul Porter for Tech Talk with Paul and Al. And it looks like today we're going to be working on a Panasonic reel-to-reel tape deck. Isn't that right, Paul?
Well, this is a Technics deck, which is Panasonic technically. And this is one strange looking tape recorder. I mean, just look at it. The way it threads is unusual. Very odd look right here. It has three brushless direct drive motors, which means it's got three-phase motors with rotation detectors and drive transistors. And this is on the edge of the integrated circuit age. This is nearly all discrete transistors and resistors with just a few ICs in it. Very, very primitive. Even has logic control, which is all TTL. This one runs and plays. Was supposed to be a simple repair, but if you watch, this tape comes down past the pinch roller. This is actually the capstan. It's a direct drive capstan turning very slowly. Comes down past the heads over this wheel, which has a LED, which would have been high-tech in those days, and a strobe marker. And this one, the speed is fluctuating at a regular rate, and you see the tensions jerking a little bit. This happens on all three speeds, not as much on the higher speeds, but the speed's not stable. And I've been studying this thing, trying to figure out what the problem is. Haven't found anything to put my finger on, but I figured out yesterday that if I pull out the pitch control and go to manual speed adjust, I've got steady speed and steady tension. This doesn't make any sense because all going from automatic speed to manual speed does is switch from a crystal-based oscillator to a simple flip-flop variable oscillator. Why it's doing this, I don't know. One person said, why don't you just put a motor in it? Well, that's easier said than done. Let me turn this thing around. It weighs a ton. All this old stuff weighs a ton. This thing really weighs a ton. Look at the size of the capstan motor. That's this. The reel tables are also the same thing, brushless, three-phase, DC motor. So there's no belts in this to be changed, except there's a belt on the tape counter, but that doesn't count. And it's hard to troubleshoot because you can't get to anything. But here are discrete transistors driving the motor. There's a bank of transistors there driving the reel tables. There's the power supply. And the audio's down here, and we don't care about the audio at this point. So this has been an interesting troubleshooting job.
Now, is this up here just for changing voltage or something?
That's the remote control socket.
Oh.
And it's shown on the schematic someplace. Schematic on this one I cannot find. I've got a similar model with a similar set of circuits, trying to troubleshoot between the two. So it means the connectors aren't numbered the same and slight differences in the circuit. But there's the motor, FG coil, which gives you a pulse telling the circuit how fast it's spinning, and drive coils and direction detect coils and some other stuff. Love to find a description of theory of operation description for this, because they're putting a 50 cycle signal into this motor, probably using that for phase detection to get direction and speed of the motor. It's got markings about direction change and forward reverse detection, but this motor only runs in one direction. And what I'm seeing, I think, is right here. There's a pulse occurs every time that speed fluctuates, and that's called the forward reverse change transistor. And it comes from a flip-flop right there. And that flip-flop also has an output to the reel tables, which I have not found that point yet, to see if we're getting a pulse probably detected in error, saying the motor's either going the wrong direction or it's going too the wrong speed, or it's just for no apparent reason it's outputting this momentary reverse or hesitate signal, causing that jerk. But why, when you go from automatic speed to manual, going from this oscillator to that countdown circuit, does it start jerking?
Okay, so for that reason, you could probably say that the little LED sensor is running over there and producing a fixed signal that's picked up by some sort of light sensor.
Yeah.
It determines the speed of the capstan and the speed of the tape. You would probably have to say that's okay, because
yeah,
if it weren't, it would be not working on either one of these.
Well, you can hear when you play back the tape that it's jerking. That the speed is fluctuating. It's very annoying. And that little LED normally would have a 60 cycle neon lamp or a 60 cycle LED with that strobe to indicate speed. Well, they obviously changed the frequency of the LED when you change speed so that the same wheel stands still at different speeds. But apparently this is fed by a stable oscillator, maybe not the same oscillator that does the speed control. But this one's proven to be a real brain teaser, especially since you can get stable manual speed, but you can't get stable automatic speed. It should be one and the same.
Have you actually put a scope on the oscillator?
I have. I've got a scope right there, and it produces an equal duty square wave off of the countdown IC, and it's supposed to be 64 cycles, and it is. And I can switch it to manual speed, and I've got the same duty, the same frequency, different duty cycle. That is the only difference. It's a narrow pulse, but the spacing is still the same.
And you don't see any jumping on that one that's bad?
No, everything is stable, but it's getting up here, and this is where it matches FG to frequency with a gating pulse, and gets an output that goes down here that controls the speed of the motor. And right in here is where we're getting this pulse rising that's not supposed to be there. So that's tonight's brain teasers to figure this thing out.
Yeah.
But
well,
it's going to be interesting.
It's all discrete solid state, so that means you could get to every little part.
Yeah.
Even in this chassis.
Yeah, I'm probably going to find that it's got an electrolytic capacitor open or leaky. It dawned on me I might ought to look at the power supply, see if there's some hum or ripple riding on one of the voltage sources. Anything that would cause it to erroneously output this pulse, which obviously isn't supposed to be there. When you go to manual mode, the line stays flat. You put it in automatic and it goes dip, 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 dip every time the speed fluctuates.
And have you looked at any possible adjacent circuits that might be involved with the automatic mode?
I was trying to figure out whether it was the real tables telling the capstan to slow down or vice versa. And best I can figure, the capstan speed is monitored by the real table motor, so that as you run at a higher transport speed, the real motors know to keep up. That's why you've got this flip-flop. It probably serves the same purpose to either stop the motors, or if this was a reversible, records in both the direction machines, auto reverse, that it would know which direction the capstan was running and would therefore also reverse the real motors. But this is a single direction machine.
A pretty good analysis so far, except we don't know what's causing it.
I've got a great analysis. I just don't know why. Because I have not put my finger on the problem yet. And you can see troubleshooting this, there's only a handful of test points. There's some of them up in here. They're not readily accessible.
So are these boards fold out in any way?
You wish. No, they did not design these to be worked on.
So it's one of those things where you have to dig in there, maybe put a little bitty wire on something, and then...
Well, it may come to me just dismantling this and getting the power supply board out, and this board out, and this board out, and taking an ESR meter and just checking capacitors. Now I can go over here to, this is the real table drive board, and I've got a connector, which gives me access to that pulse. And I've not been able to figure out which pin to go to yet. And
but But
There's no test point.
you've been able to find a pulse that, or a signal that shows you the problem.
Yeah, I got real lucky. I got lucky on that and found that early on. Let me see if I can find the point where I was at yesterday. I usually work on these kind of late at night, and the next day I don't remember what I've done. Let me see.
Ground in the scope.
Ground the scope, yeah. And right there is a test point which gives me a pulse that corresponds to that fluctuation in speed.
So would that normally be like a DC?
No, let me go to manual speed.
So it doesn't move.
And it doesn't move.
So what is that? Where's that on the schematic?
That is test point 909, which is one of these sample pulses right in this area.
And so can you backtrack that pulse?
Let me see. No, 909 is right here. That's the base of this reverse forward change transistor. And that's in the drive circuit going to the motor. These transistors drive the motor. This is the base circuit driving them, and this is the position detection coil, which obviously is an induced signal that comes in to tell these transistors which sequence to turn on, off, on, off, on, off, or off, on, off, on, off, on, depending on the direction
Could it be
running.
as simple as some dust or something in a pickup sensor?
I was hoping that it was just this switch on the back of the speed control maybe wasn't making right here. And I've cleaned the switch. Doesn't seem to be any difference. And it's funny, you're going from this oscillator to that oscillator. That's a no-brainer. And I can go to the test point right here and see the difference. And this switch, this is the volume control, potentiometer. And you adjust it, I don't know for what, so that you've got a little more or a little less sampling pulse.
You know, that's the thing. It's weird because you'd think switching between those oscillators wouldn't make any difference.
You would think. And this circuit says reset pulse. Okay, reset for what? And what would make it output a pulse that says, hey, you need to stop or reverse? Maybe
it's got some sort of limit on speed that makes that trigger.
You know, if you ground that test point, it doesn't reverse the motor. The motor loses its torque because you're obviously getting rid of the bias on these. But it doesn't make the motor reverse.
This is a real tough one.
It is a tough one. Yeah. This is what we used to do back in the old days before replaceable circuit boards and ICs and modules. We did component level troubleshooting just like this. And they paid us about $4 an hour.
Which was more money then.
Money was worth a lot of money back then, but we spent our days troubleshooting amplifiers, tuners. This would have been the highest tech thing we would see. This is probably about 1979 or 80. I haven't checked the date on it. This would have been super high tech. I mean, these servo drive motors, brushless motors, which are basically DC three-phase motors. You have three coils and a permanent magnet, and by either using photo interrupters, photosensors, Hall elements, PG coils, you find a way to switch these three transistors on off in series to pull that rotor around like a three-phase motor.
But you have a lot of control doing that.
You have a lot of control. This machine has a wow and flutter spec that's like 0.00 something. I mean, just almost no wow and flutter.
Well, see, these were considered a big deal.
This would have been a $1,000 tape deck.
Which by today's money.
In 1978, which would have been $5,000 or $6,000. Yeah, very, very high tech, highly desirable. It's neat because this one it's a 2-track machine with professional audio jacks, XLR inputs and outputs, but it's got a switch. It has a 4-track playback head, so that you could play your existing 4-track pre-recorded tapes or tapes made on another deck, but it records and plays in 2-channel half-track, which would be professional, and it does it in 3 speeds, including 15 nips, 7.5, and 3 3/4.
So this would be a mastering deck.
This could be a mastering deck or a deck for a music major or somebody with perfect pitch. You know, some really uppity critical person or an audiophile. Yeah. And the owner says, I don't care, I've got to have it fixed. So, well, it's going to take a while. Some other stuff's going to have to wait while I work on this one, but he wants it. So that's my project for tonight, is to see if I can figure out why manual and automatic are doing what they're doing.
Well, see, what I'm thinking here is, you know, for even today, if someone wanted a really good, clean analog audio recording, they could use this, like in a concert hall, or is the person that owns this like a musician or a conductor?
Yeah, well, this is going to be resold. This belongs to a broker. He's going to resell it. These are a hot item right now. I don't know if anybody's lugging these things out and trying to capture live music with them. I'm sure probably there are some people doing that. Most people that buy these are putting their CDs on tape, or they're finding pre-recorded tape. And there are people getting their hands on old masters, I'm sure. Some people just love the sound of analog open reel and are recording, I don't know what. They put I used to put all my records on tape to save the record. And there's a big interest in analog and being able, I guess, to experience it and experiment with it and just say, hey, doesn't this sound great? And look at this machine. This is a machine. We don't have machines anymore. We have little plastic things in our hand that have more circuitry than God ever imagined, but we don't see how anything happens. This machine, you can see how it happens. And I can look at here and see how the machine does what it does.
Well, you can tell it was real well built.
Oh, yeah. Oh, yeah. Technics was second only to TIAC and Pioneer, and of course Ampex on tape recorders.
Well, there was that other one. What was that fancy one that?
Well, there was a Kai and Sony.
No, there was another one for film recording and.
Oh, Nagra. Nagra's in a world by itself. If I ever get my Nagra back from you know who, we'll have to do a little video of that. It is something to behold. But this is a very fancy schmancy tape deck that's eating my lunch. And it's been eating my lunch for about 3 days now. I keep hoping I will wake up from my nap and the answer
get an epiphany.
The answer will come to me, and sometimes that happens.
Yeah.
This one I'm still.
Well, see, it doesn't have any obvious indicators.
No.
And that will just, you know, and so lots of times you end up pulling the boards and checking all the caps.
I thought when I found this phenomenon, I said, okay, I've got it. I haven't got it. Because if it will work with a variable frequency oscillator,
it should work with.
If this crystal controlled countdown, and you know what that is, it actually has 3 counter settings, and it gives you 3 outputs. And it's 64, 128, and it's written on here someplace, whatever the frequency is for this function. I thought, well, if it'll work with this, it'll work. Even if this is off frequency, it'll still work. Now, if you defeat the sampling pulse in standard speed mode, this is the killer. The searching stops. It just runs a little off speed. It's something with this sampling circuit where it compares this frequency to this frequency, and this pulse is used to sample and see where on the ramp. I knew where that oscillator point was.
Well, you know,
they generate a sawtooth wave.
I had to put my glasses on, but is that a tuned circuit anywhere in there?
Only right there. There's a crystal in this counter, and there's also a countdown. The PG coil.
So basically, it's just a comparator.
And there's a count. Yes, it's a comparator. And let me figure out if I can figure out where that ramp is. Let me just hunt for it for a second. Because there's a sine wave in here. It's not that one.
Maybe we could find a little glitch in the signal for comparison, but that is but you know the strangest thing is you would expect either oscillator to make it work bad.
You would. You would. I'm just.
Unless it's a frequency dependent thing, if the oscillator.
There it is. There it is.
If the oscillation frequencies are that different.
These two test points, and if I had this dual trace scope, I've got one channel out. Otherwise, we could do a really neat comparison. Okay, there is the sample sine wave. And we should be able to take that, and this is the test point next to it. I get my little hook to hook in the hole there. And there are the sample pulses, and these will sample that ramp. And if you vary the speed of the motor, these move back and forth on this slanted ramp, and they sample the voltage at that instant on that ramp.
And then they make a comparison.
And that resulting output voltage is the error that's used to speed up or slow down the motor.
Right.
And this is obviously sampling, but for some reason it's outputting some erroneous information, or a circuit downstream is overreacting. And
because you don't see any obvious aberration in the sample or the ramp.
The sample looks good, the pulse is good, everything's like it should be, but for some reason you get down here and you've got this flip-flop which says constant something, what is it? Reverse forward detection, here it is. Absolute value circuit. This I've not figured out. This is the speed error comes in, and these detections come out, and you've got to...
Well, see how those transistors are put in the crisscross pattern?
Yeah.
And what that is it's taking a balance. It's looking at the balance, and it's and so whenever the bias shifts...
Something, and it's the circuit making these two transistors go blip, blip.
Yeah. Well, a capacitor being whacked in there would throw that off.
But why does it blip, blip when it's got one signal and not blip, blip with the other?
Well, how off frequency is the two oscillators?
How off?
How different? Do they make different frequencies?
No, they're the same.
Okay.
They're absolutely the same.
That makes no sense.
One's variable, one is fixed, but something down here, either here or here, I can defeat this, so I get a constant voltage to this motor. Speed is constant. There's something, I've got to get to this point right here.
Now see the little dotted line here going around here?
Yeah.
What is that supposed to...
That connects switch, pot, switch, pot. That's the back of a volume control. But I've got my speed error right here, and goes into a differential amplifier. They love differential amplifiers. And it goes on into this, and then into that, and goes on into here.
So that's used for precision.
This test point was not installed.
Precision speed control 101.
At its time, it was very precise. Now, a 60 cycle motor, here's a good point. In just a few years ago, the AC line signal coming out of your wall outlet was 99.9% accurate. 60 cycle AC. And they have figured out that we are no longer dependent on that signal for clocks or turntables or anything, and they figured out they can let the frequency drift, that it really doesn't matter anymore as long as all the generators on the grid are locked together. So I think we're now down to like 59.9 speed-wise.
But it'll go up and down.
It can go up and down. And if you watch the strobe wheel on a good turntable, it used to be rock solid. And now they'll sit there and they kind of dither.
Yeah, so much for synchronous motors.
And you think you've got a bad motor, but no, it's just the AC we're getting is crappy.
Yeah, and so Hammond organs aren't accurate anymore?
Oh, don't even get me on Hammond organs. I got a story on that I'll do in just a second. This machine, since it doesn't depend on the AC line, would regard rock solid regardless of line frequency. Many years ago, Hammond organs were very popular with circuses and traveling shows. And used to know somebody that was in a circus, a real circus. They had a Hammond organ on a trailer, and they took it on the circus circuit to the south. And they learned that the little local mom and pop generating stations couldn't be trusted for frequency. And they frequently had to use their own generator, which you really couldn't trust. Hammond made a tuning fork oscillator based amplifier to drive the motor in their organ. Two 2A3s, a couple of 56s, you know what those are. It's like a 25 watt amplifier with a metal tuning fork, humming at 60 cycles, and driving two 2A3 power triodes. You started the organ on whatever voltage you had, and then you switched it over. The run voltage was provided by this frequency standard tube type mechanical oscillator power supply, so that your Hammond was on pitch, even if your generator was fluctuating, which generators would, or the local line frequency was 50 cycles, not 60, or the local generator was sloppy. I have looked and looked and looked for any reference to this unit and can't find it anywhere on the planet. But I've got one. I just don't know when it was made or where it was in the catalog or a schematic. It's a neat thing. Got it from the original owner who explained why they had to have it back in the day.
Well, see, loosely connected back when you had two radios in your car. You had something called a vibrator, and it was basically
that was also a 120 cycle mechanical oscillator to step DC up to AC to get the voltage for the plates in your radio.
It was just sitting there vibrating mechanically.
It made a lovely soft humming sound. Turn the radio on. And then the tubes would warm up and the radio would come on and you'd have KLIF, top 40 radio. And car radio sounded good in those days, too.
But they quite often went out, the vibrators.
Oh, yeah, they wore out. Yeah. I take them apart and file the contacts and put them back together. I still do everything. Somewhere there's some GE radios around here that ran on a 2-volt lead acid battery. And they had a vibrator, a little custom built one GE made for the B+. You can't get them. They're hell to rebuild. I've got to get one working because this radio is gorgeous, but it's got a vibrator power supply run on a rechargeable wet lead acid battery, not a gel cell. You put water in this battery,
just like a car battery.
Like a car battery, yes. So I'm talked out. This is a toughie.
Well, this is the part 1 part.
This is part 1. We find the answer, we'll do part 2.
Or you can tell us. But this has been fascinating, and everybody has something to think about.
This is a lot to digest.
I'll put this on YouTube, and maybe someone will give you an idea.
I wish.
Hey, YouTube folks, give us an idea about how to fix this.
Yeah. Oh, this is an RS 1520 Technics. I'm using an RS 1500 schematic that I got off the internet.
You know, it could be, well, your schematic differences is what's causing your problem.
It would be a little easier to troubleshoot if the schematic was accurate. This one is like 90%.
Yeah, so there might be a little difference in the schematic that is throwing you off.
I look at several different models, and they all have this circuit. But they're arranged differently. The connectors are numbered differently. There's subtle differences. Now, we talked about this being early integrated circuit. The last one of these they built has ICs. Power ICs in place of this. More ICs in the speed control and the logic. This is all TTL logic. You know, push buttons.
See, but you don't know that this schematic is accurate.
It could be off a little bit.
But that little bit could be causing a problem.
I have done some pioneers where the schematic and the unit bear almost no resemblance to each other. So many changes. But yeah, this is a toughie. I thought I'd find the motor had one dead winding. You know, something obvious. No, this motor is smooth and strong. Just that little glitch.
Well, YouTube folks, why don't you give us a hint if you have an idea. Or if you happen to have the correct schematic, give us a communication on this video.
Yeah, be kind and share.
Okay. Well, that's going to be it for tonight.